Excuse me. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Blast off. Welcome to EE123, Lecture 6. Woo! Such a high-pitched voice. Okay, how are we doing? Happy Monday. Happy Monday. It's the beginning of the week. Eager young minds. Learn new stuff. Frank, any announcement? No? Okay. Homework 1 solutions posted. Self-grading due Tuesday. Yes? Homework 2 is due Friday. We're going to have a homework slip policy. Lowest grade of homework will be dropped. And I'm only telling this 2 weeks in. So, like, you get you stayed so far. SDR giveaways Thursday in the lab. So we're going to start giving those SDR dongles, or we'll try to do maybe on Friday lecture as well. And worst case, next week through the labs. Effectively, you have to get your dongle by the end of next week. Don't forget, ham radio licensing lecture 2 is on Wednesday, 6:30. I think 8:30, but in Corey 521. Okay, yeah. Is self-grading always going to be on Tuesdays from now?
Yeah, for now, yes.
For now, yes, but not always. Could be, yeah. Okay, any more questions before we move on? Today's the second lecture of my favorite topic, which is the DFT. It is a wonderful transformation, and it's an amazing tool that's been used for decades so far in order to make everything that you have here work. Okay, so we're going to go over this, but before this, let's just go to something a little bit more ancient. And I don't know if you've seen my background, my desktop background, but it shows an image of the cosmic microwave radiation that was generated through this Planck satellite. So it's actually recent data that came, I think, about 2 or 3 years ago. There are 3 missions so far to map the microwave background radiation, and that was the third, and it brought it at a much significantly higher resolution than before, but also gave some information about the polarization. It turns out this cosmic microwave background radiation is also polarized. So what does it have to do with DSP? Well, because people are trying to measure this, to use this measurement in order to infer information about how galaxies are formed, how stars are formed, what happened at the early time of the universe, by looking at the statistics of this map. This is an amazing thing. By the way, there's an interesting story about this, about people that are really confident about the equipment that they built, the system that they built. It's been hypothesized for a long time that there is some remnant radiation from the Big Bang. But in the 60s, there was a team from Princeton that was going to build a telescope, a radio telescope, to basically search for it. A team at AT&T Bell Labs was building a radio telescope for other purposes, mainly for satellite communication, but also just to look at the skies. And when they started measuring, they could not account for a very small level of noise that they were seeing in the signal. And they were so confident about their system that they realized that this is actually something that they're observing, not just noise in their system. And no matter where they point it, they saw it, which led to this discovery, which is quite amazing feat of engineering. Okay? So things that people do with this is analyze the statistics of this, but you can think of, there's certain statistics that it needs to obey from quantum mechanics and so on and so forth. But let's say there's some galaxy between us and the universe, and it creates this gravitational lensing, which then changes a little bit that statistic, so you can use that to discover all those effects. So there's a lot of interesting things that people try to do this. But it's kind of like existential type of work. So it's pretty amazing, and you can read all about it when you look for the cosmic microwave background radiation. Okay. Moving on. So last thing, we talked about discrete Fourier transform. We said it's same, but different than the DFS. But by the way, you remember my kids were here last Monday? So I asked them, so how was the lecture? And they go like, well, Abba, you basically the way you speak is more like like omega. Like, okay. But we still love you. There you go. Okay. Like. All right. So it's same, but different to the DFS. It is a sampling of the DTFT, which is amazing, but there's some subtleties with that. When we're going to talk about it a little bit later. And then we started talking about the properties of the DFT. Today we're going to talk about doing linear convolution with DFT. Now, convolutions are one of the most important operations that people are doing today even. If you think about convolutional neural nets, that's what is the hot thing that's happening right now in the world of AI and machine learning. Convolutional stuff, right? So again, it's convolution operators. Very important type of operation. It's used almost everywhere. We're going to talk about linear convolution with DFT, and then talk about the overlap add, overlap save method to do fast convolutions. Normally, convolutions would be expensive if you're convolving with a large kernel. But as it turns out, using the DFT or, in fact, the FFT, you're able to do it much faster. Okay, questions? No, I didn't really say anything. All right, so let's move on. So what is... Okay, so with the DFT, or as you will see, things kind of seemed circulant. Remember? When we sample, things are kind of circulant. So periodic, sync. Everything is kind of like wraps upon itself. And as it turns out, that's one of the features or the bugs in the DFT that we need to deal with. But let's talk before about what is a circular convolution. So a linear convolution, you would convolve something. You will have a signal, and you would perform the usual convolution by multiplying and adding and then shifting your signal. A circular convolution is similar, in the sense that you do exactly the same. You have one signal, and then you flip it, and you multiply and add with the other one. But when we're talking about finite sequences, we're going to think of them as wrapping upon themselves. So instead of being linear, we're going to kind of fold them around and connect them at the end. So when you're performing these convolutions, when you reach the end of the sequence, you're going to start, or the beginning of the sequence, you're going to start taking measurements from the end of it. Okay? So that's a circular convolution. And it's defined in the following way with an n, because we're going to perform these circular convolutions over certain sizes. Much like we did a DFT on a certain size, we're going to perform linear convolution on a certain size. Okay? All right. So note that much like linear convolution, circular convolution are commutative. And here's how you really compute it. Let's say you have a sequence x1 and x2, and we want to compute a circular convolution of size 7. What the first thing you do when you do a convolution, you take one of them, you flip, and then you multiply and add. So when we go and flip this guy over here, we're going to flip it circulantly. Okay? It's going to flip and wrap to the end of the sequence. Okay? Because it's always on the side. In this case, it's only going to be on size 7. Okay? So we're going to circularly flip it and then multiply and add to get y0. Okay? So multiply, add, and that will give us y0. Then we're going to shift it by 1, shift those circulantly, multiply and add to get y1. Shift it again, multiply and add, and do it again. Now, yes, if you have a circulant mind, it's easy to do this. But if you have a linear mind, then another way to do this is basically replicate your signal with a period of 7 and perform kind of a linear convolution, right? You then flip it this way and then multiply and add. And so this basically makes sense to do a equivalent to a periodic convolution of a one period. Okay, does this make sense? Okay, great. So then you just move it around. By the way, what happens here, if you see that the measurements of y0 now is going to depend on x6. Okay? So y0 depend on x6, right? So that's usually not happening when we're talking about linear convolution. Okay, so you shift it around, shift it, look at this beautiful animation, and we're going to reach 6, and that's over. Sad. But the calculation is done, so you can be happy about it. And the result of this circular convolution is basically the following signal. Okay, so we got some smooth version of that signal, right? We got two rects. They're convolved with each other. We're supposed to get a triangle, but we didn't. Right? We didn't get a triangle. We got something else. And the reason we got something else was because we did not perform a linear convolution. We performed a circular one. Okay? So it is not the same. Now, if we go back to the properties of the DFT, there is this property of a circular convolution. So if you got the circular convolution between two sequences in the signal domain, if you perform the DFT, then you've got multiplication of the DFT of those two sequences. Okay? So it's similar somewhat to the DTFT and the continuous time in the sense that convolution corresponds to a multiplication in the frequency domain, except we have to remember that now it's circulant convolutions. It's not linear convolutions. Okay? It is, and as it turns out, it's very useful to compute linear convolution using the DFT. Huh? It is a circular convolution, but we're going to use that circular convolution property in order to compute linear convolutions. Right? Okay, so now if you have multiplication in the sequence domain, it also corresponds to a circular convolution in the frequency domain, and then you have to divide also by n. And you have to remember this because we chose to compute a DFT in a particular way. Okay? If it was orthonormal DFT, then it wouldn't be that way. Okay. So that's great. So circular convolutions are great if you need them, but generally we don't, right? Like, we like things to be nice and linear. If we want to filter a signal, we don't want the end of that signal to interfere with its beginning. Here's an example. I have an image, and I want to filter that image. So it's a two-dimensional filter, but just imagine that we're just going to filter along one dimension. If we're going to perform a circular convolution, the right-hand side of the image is going to be influenced by the left side of the image, and it doesn't make sense. Right? It doesn't make sense. Okay? So this is not a property that we want. But unless it's a circular panorama, which is then, yeah, absolutely, that's great. Yeah, that's a good idea. That's a good idea. So you can, but like even phones, they let you only do like 180s. The what?
Facebook has like that 360 video feature.
Oh.
Angle your phone and it shows like a different part of it.
Okay, so we found a good use for circular convolution, but other than this particular, edge cases, this is not necessarily what we want to do. Okay. Now, why do we even care about using DFT for convolutions in general? Is because we have this beautiful thing called FFT, which we haven't learned about, but you've probably heard of. It allows you to compute things at an order of n log n as opposed to n squared. So you can use the FFT or the DFT or the fast Fourier transform in order to do this. Okay? So we want to use this property. And how do we do this? So using the DFT, circular convolution is easy. Okay? It's a multiplication. By the way, if you think about it, what does it mean to just that it becomes a multiplication? What does it mean? Remember we described the DFT as a matrix, right? So if you describe the DFT as a matrix, you can also describe a circular convolution as a matrix as well. So if you have some vector or some sequence of finite length, you can perform a circular convolution on it by multiplying it with a matrix that performs a circular convolution. Okay? So you take your impulse response, you order it accordingly in a matrix to perform the operation of a circular convolution on a sequence. Now, what does it mean, really, that now the circular convolution that is expensive, because now it's maybe a full matrix, can become a multiplication? Just a pointwise multiplications. What is a pointwise multiplication in terms of matrices? It's a what? Matrices. I want to take a matrix, and I want to have two sequences, and I want to do a pointwise multiplication between these two sequences. How do I write that in matrix form? That would be an inner product. But then you end up with a matrix. Okay, so you put one sequence on the diagonal, so you create a diagonal matrix, right? A diagonal matrix that multiplies a vector. Now, we have a circular convolution, right? And then if we compute the DFT, now things become multiplications. What does it mean about the DFT matrix? And what does it mean, what happens? You can use it to diagonalize circular matrices. So then we can think about what are the eigenvalues of circular matrices and so on and so forth. Okay, so we'll get to that. Okay, so it all makes sense. Okay, from a linear algebra point of view, from an algorithm point of view, but it all comes down to the same thing, but with a different language. So we'll get to that. Okay, so linear convolution is useful, not circular convolution, except for Facebook and except for panoramas. what we want to do is we want to show how to perform this linear convolution with a circular convolution and use the DFT to do this. Okay. So what we're going to do is the following. We're going to start with two non-periodic sequences, x of n, which has a certain length. We'll call that length L. And the other one is h of n, the impulse response, with the length of p. Okay? So if we want to compute the linear convolution, we can compute the linear convolution by the usual equation. And if you think about what is the length of the result, what is the length of the result? If you have an L and a P sequences and you convolve them together, what's the result? Almost. That's in continuous time. L plus P minus 1. Okay? So again, like, if you remember in continuous time, you've got an L and you've got a T, then it's L plus T, right? But in discrete time, it's L plus T minus 1, because now it's discrete. Remember, small stuff, but then you end up with spikes in your data if you don't account for this. Okay? So remember this. Subtleties when we talk about discrete. Okay, so the length is going to be L plus P minus 1, so y of n is non-zero for n less than equal to L plus P minus 2, and then greater than 0. Okay, so the length is L plus P minus 1. In order to do this, you need L times P multiplications. Okay, great. So we want to express the same operation using circular convolution. So the way to do this is, first of all, we're going to perform zero padding of our sequences. Okay? We're going to zero pad our sequence, the x sequence, by p minus 1 zeros. So basically, we're going to reach L plus p minus 1 length sequences. So we're going to zero pad by p minus 1 and zero pad the other one by L minus 1. So both of them are now L plus p minus 1 long, only with zeros at the ends. Okay, so both sequences are that length. Okay. So now what we can do then is compute the linear convolution just using a circular one. Okay, now that our sequences are long enough, they're zero padded. Whenever we can perform a circular convolution, we are actually going to perform a similar thing as a linear convolution for the original sequences. So if you look at the previous example, if we have a sequence of length 5 and a length 4, we're going to zero pad them to length 5 plus 4 minus 1, which is 8. We're just going to put zeros. And now when you're going to do the circular flip, it doesn't overlap with anything. Okay? It's just going to overlap with the zeros at the end. And you're guaranteed that it's only going to overlap like with that sequence at the end. Okay? I probably don't need to add them because I do that anyway. Okay. All right. So in this case, the linear convolution is equivalent to the circular convolution. Fantastic. That's great. Okay. So there's no overlap here. We solved the problem of this overlap. Okay. And basically, this is all really you need to do. You just need to make sure that there's zeros at the edges so that the zeros need to be more than the extent of one of those, of one of the filters. Okay. So now, in practice, if we want to implement such a convolution, okay, using the DFT property, all we need to do, if we want to compute this, we need to zero pad those two sequences, and then perform a circular convolution of them. But then, of course, it can also be written sorry. I was making new slides yesterday. By the way, this is an opportunity for you. Opportunity to make money. So I'm making new slides. And so I was thinking, where's my slide? But it's going to come. Okay, so all you need to do is take the DFT of the zero padded filter, and then take the DFT of the zero padded sequence, multiply them together, and then take the inverse DFT of this. Okay, great. So the advantage is that we can now compute this operation in an n log n, the operation n log n number of multiplications, which is great. But there's a really inherent drawback here, and that's usual for everything related to computation. Okay? There's an inherent thing here that we have to wait for the entire sequence to come if we want to do that. Okay? We want to convolve something, we have to wait for X event to be done, then compute its DFT, then compute the DFT of H event, multiply them, and take the inverse DFT. Okay? And that's the inherent trade-off between memory and computation. You need now storage of memory to store this and then be able to do this computation. It costs you memory. Okay? This makes sense. And what else it costs? Let's say I have a real-time system, okay, in a car, and I want to use the DFT to compute, filtering. Okay, so person drives the car. The computer in the car records all the things that happened, and then once you get home, it's going to filter everything, and then it's going to. You see what the problem is. Okay, you cannot use it for controlling stuff, right? Because you've got a huge delay. You have to wait till the sequence ends and then do that. Okay? What? No way. Real? Nice. Oh, wait a second. You know what happened? You see the bottom? Does this work? Hey, where did you go? It was there. Does that count as a typo? Vote. Let's vote. Typo or not? Who says typo? Who says not typo? They're not very collegial, right? Like, what does it cost you to say that's a typo? What does it cost you? It just cost me. You get the $2. Last name, remember? U-K-U-M. $2. And you should talk to your friends. It's not a way to support. Okay, so huge delay. That's the main drawback, okay? So what we want to do then, I gave you a hint. So what will be the solution to do this? Let's say you do. No, let's say you have a real-time system, right? What's the solution there? Like you really need to get results in real time. That's a problem, right? Well, how do you pick up this 30 milliseconds? How did you pick up this 30 millisecond at a time? Like, well, why 30 milliseconds?
I mean, I'm just giving an example.
Okay, that's exactly what I'm trying to ask. Like, what?
Because sometimes 30 milliseconds is not enough.
Right.
Everything you try to do in real time with computation incurs some kind of cost, just because it takes time to add, even if you're
Sure.
not going to have it exactly real time, even if you're using official real time.
Okay, so it's going to only depend on the application. What can you afford? Okay. Some system can afford a second. You take a second of sequence, okay, and then filter it. Some other systems, 30 millisecond, maybe in a car, that's fine. Some other systems, like, controlling like an MR system, you have to do that way faster than 30 millisecond. You need to do it microseconds, okay, or things like that, or some, like high-speed, digital systems that operate at a gigabit range. I mean, depends, right? It depends. But then there's always a certain, I mean, depends on what the rates of the sample coming and what's your system limitations. This is what engineers do. You can afford a certain size of a buffer or a delay to come up with an output. Okay? Yeah.
So the length of your sample will also determine what frequency we can look for, right?
It's the length of your samples are gonna depend on your. Well, it depends. We'll talk about this. We'll talk about it.
That too, because it seems really counterintuitive that with like a small sample
It's not the rate of the sample. It's really, so we're actually not going to just do a block. We're going to do the whole thing, but we're going to divide our sequence into blocks. And then perform that operation on these blocks. And the question is, when do I start needing to put samples back out? How long does it take? So I need to collect a few, and then perform a calculation and put those blocks out. That's what's going to happen. And that is going to be a certain delay. Okay? So this is exactly what we're going to do. Okay? And that's going to depend. So the problem is that X event can be really long, and it can be sometimes infinite. Okay? And we have an impulse response of a system, let's say an FIR system, that has a certain length P. Okay? And that's its length. And we want to perform these convolutions. And we want to take use the advantage of the FFT and DFT in order to do this. Okay, so the approach we're going to do is we're going to break our signal into small blocks, as opposed to waiting for the entire thing. We're going to allow a certain time to accumulate and then perform the operation in blocks, which is potentially going to be almost instantaneous with respect to that calculation. Then compute the convolutions, and then once we have these blocks, we need to combine them in order to get the result of what will be a continuous block. Because there are going to be issues then when I break something into blocks. What's going to be at the end? Right? I need to make sure that the operation that I'm performing is not limited by the fact that I'm taking these blocks. Okay? So in the block convolution, if I have, let's say, an impulse response, which is just a moving average of length 6. If I have X of n, which is length of 33, if I convolve these, a linear convolution, I'm going to get a result with length of P plus, one P and the other P. So 33 plus 6 minus 1. Okay, so 38. Okay, so that's going to be its length. So here's the method. So how would you then do that? Like, how do you combine, how do I break stuff, perform a convolution, and then combine that in a way that it's transparent to the block size or to the blocks that I picked? What would you do? You'll see it comes out everywhere. Like, this is a buffer, right? Like, you've got this buffer that comes in. If you think of embedded systems, or even on your computer, I mean, you'll have some device that throws samples into direct memory access, into some array in your memory, and then it's going to be filled up. When it's filled up, puts an interrupt, and then starts filling up another buffer. When it's done, it puts an interrupt, fill in the first buffer. That's how a double buffering system works. And then if you want to do some signal processing in them, you get one buffer. Once you get an interrupt, you get the access to that buffer. You do some operations to this, then you get another buffer. You do operations to this. But you want that to appear as if it's one constant thing. How do you do that? What? I like the overlap thing that you said. I like the overlap. So we have to account for some overlaps. Okay, so this is exactly what we're going to do. And there's two methods that people are kind of using in order to do this operation. One of them is called an overlap add method. And the overlap add method, you decompose a sequence into non-overlapping segments. Okay? So now we're going to decompose our X of n into a lot of small sequences that are X sub r, indexed by r. So r equals 0 is the first block. R equals 1 is the second block. R equals 2 is the third block. and so on and so forth. If you're a MATLAB person, r equals 1 is the first block, so on and so forth. But we're going to use the 0 thing. And what it does really, it crops, chunks, non-continuous, non-overlapping chunks of x of n. And then I take a chunk, I take it away, and then I put zeros and think of it as an infinite sequence. Okay, that's x sub 0. Okay, I take a chunk from 0 to L minus 1, and then put it here, and then put zeros everywhere. And then x sub 1 will be take a chunk from L to 2L minus 1, take that chunk, put it in exactly the same place, and with zeros. That's how it's written mathematically. Okay, so all these are chunks that are 0 elsewhere except where the chunk is. And for this case, the input signal is the sum of these segments. So if I just sum over these r's, I'm summing over non-overlapping stuff, and hence you get back your sequence. Does this make sense? Okay, I just break x of n, take like a chunk, put it here, and assume that everything else is 0. Then I take this piece of the cake, move it over here, and then 0. That's the second sequence. And then that part, zeros. Okay? So now if I sum all these pieces together, I've got zeros where there's signal on the other ones. And then they just sum to be x of n. Okay? So now what I'm going to do is I'm going to perform the convolution. Okay? So if I have x of n, the output of convolving with that x of n, so I'm going to y of n, that's the convolution between x of n and h of n. It is also, because of linearity of the convolution property, it's the convolution, it's the sum of the convolutions with each individual segment. Does this make sense? Okay. If x of n equals to the sum of r's, then if I convolve with this, I can convolve with this. Okay. Now, each output of each segment is not going to be L long anymore. It's going to be L plus P minus 1 long. And now I've got overlaps in the outputs of the convolutions. Now they overlap. Okay? Yes?
For the previous slide, when you have the length of each block, should that be R plus 1, L, and then minus 1?
Less. Nice. It's not less than equal, but it's less. And yes, you're absolutely right. Here it's, yeah. Does this make sense? Okay. Haha, that's a new slide. Thought about it. Okay, so now we're going to do this. But the thing is, we started with non-overlapping blocks that we can add together. Now we end up with overlapping stuff. Okay? Okay. So now we can compute the convolution using linear convolutions using the DFT. So here's what we need to do. Okay? We need to compute these convolutions, right? We need to compute these convolutions. And these convolutions of each segments of length L with a filter of length P. So here's the algorithm. We're going to zero pad x of r of n, each one of these sequences, to length n. Okay? N would be L plus P minus 1. We're going to zero pad h of n to length n and compute the DTFT, the DFT of this sequence. And we have to do this only once. Why? Why do we have to do this only once? What? Yeah, it's not changing. It's not changing. H of n is not changing, right? That we want to convolve with this FIR filter, right? So that's not changing. So we just can compute it and then store that. So we don't need to do it over and over again. Saves a lot of computation, okay? All right, so now we're going to compute the convolution between each of these subsequences with H of n by using the DFT property. So we're going to take this we already computed, multiply by the DFT of x sub r that is zero padded, and then after we do the multiplication, we compute the inverse DFT. Okay? and we get the result for the convolution of this sequence. Now, each neighbor overlaps by p minus 1 with its neighbor, p minus 1 samples. So what we need to do then is save some information from the previous buffer and add it to the new buffer, and that will take care of basically everything. Okay? So this is what happens. Let's take a look. So what I do is I break my sequence into non-overlapping blocks. Okay? So x of n is the whole sequence. Okay? That's the sequence. I broke it into x sub 0, x sub 1, x sub 2 that look like that. Okay? All right. Now, I zero-pad it appropriately and perform the convolution. Or in this case, I perform a linear convolution. You can do this linear convolution by circular convolution, by zero-padding. Yes? You're kind of right, except it says here y. But you're absolutely correct. And you know what? Touche. Eric, what? It doesn't count if it appears in the next one. Okay. With h of n. Okay, which I didn't show it here. It's the same. It's basically a moving average of length 6. Okay. All right. So then I computed this, and now you've got a spillover. Okay, you've got a spillover, and here you've got a spillover, and here you've got a spillover. And so the result, you have to store the spillover and then add it to the next one in order to do this, right? And then eventually you get exactly the same thing. You just have to keep track on those. And here's the thing about DSP. You have to, those indices, right? It's really important to keep track of those. If you are off by 1 when you do, these bugs, you don't get what you want. And so you have to keep track. Okay, that's another thing practically that you have to think of. Okay, so this is one way of doing this. And from a memory management point of view, think about this. Like I have a buffer, I compute this, then I have to store the end of that buffer, keep it, for the next time, next buffer that comes in, I get some result, and then I add that first buffer stuff to it, and then I move that away. Right, so you have to store some stuff and so on and so forth. So you have to keep track from an implementation point of view. The other way that people do it is they call it an overlap save method. Okay? And it's same but different. Okay? Instead of splitting the input into non-overlapping sequences, you split the input into overlapping sequences, okay? Into overlapping segments. Each one of them is going to be L plus P minus 1. So now it looks exactly the same, except you take a larger chunk. But then when you move by L. But I take L plus P minus 1. Okay? So I take a buffer L plus P minus 1, I take it out, and then the next one I move by L and then take L plus P minus 1. Then what I'm going to do is I'm going to perform a circular convolution on each of these segments. No zero padding needed. Okay? And then, as it turns out, part of that circular convolution is in fact a valid linear convolution. Part of it is corrupted from the other side, but part of it is linear. And we're just going to save the L valid linear convolution samples. So here how it works. Okay? Let's say I have the sequence. If I want to perform a circular convolution, if I perform a circular convolution, the first sample is not a valid linear convolution. Okay? Because it uses the end in order to perform that. Okay? But if I move by one sample over, now I've got zeros here. Okay? So actually this part is a valid linear convolution. And this part is also, and this part is also, and this part also, and this part is also, and this part is also, and done. So part of that circular convolution is a valid one. So here's how it works. Ready? Yep. Okay. We're going to take an overlap. Okay, all right. I was looking if there was X of N's and stuff. Okay. We're going to take an overlap, like I'm losing here, so, and that's the fifth time I'm teaching this class. My God. There's still money to be made. Okay. So I took a certain chunk out of that input. I took a chunk of that input. And then the next chunk overlaps with this one. And then the next chunk also overlaps with this one. If you add them, you don't get X of N. Okay? If you add them, you don't get X of N. Okay, so you have to watch out. Then when I'm going to compute the circular convolution is going to have some non-valid stuff in the beginning, and then it's going to have some valid stuff. This one will also have some non-valid stuff in the beginning, and then some valid stuff. And this one will also have some non-valid. But the cool thing about this, if I only take the L valid stuff, now I just need to spit it out. I don't need to preserve extra stuff. Okay, I don't need to remember what was the result in the previous time and then add it to the following stuff. Now I just take a chunk, compute circular convolution, take this part, spit it out. Take another overlapping chunk. Okay, so start increasing my kind of circularly shifting my buffer, get the next part, perform the circular convolution, take the last L, spit them out. Okay, same but different. Yeah. Yes. I'm not sure exactly what the examples actually shows here. Let's see. Input segment of L equals 16. So I picked L equals 16, which is L plus P minus 1. Okay. So it's not exactly the same size as the previous examples, but it shows, the concept of taking overlaps, and then the result will have some valid part. And the valid part will not be overlapping, and that's the point. Okay, does this make sense? So overlap and save, yes.
So the circular convolution corrupts the overlaps so that we don't have to care about them.
Right. Pretty much. Right. So you're computing something that you really don't want, but you do this in order to save computation. Strange, right? It's really to exploit structure in the problem. Yep.
So when you're at the start of the sequence at 0 sample,
yeah.
throw junk data.
Yeah, you store. So always in the beginning, there's going to be some junk data. There's always some junk data. I mean, what does it mean? Like I started with something, I'm starting to convolve. It's either I'm going to assume that there was 0 before, there's something before, but usually it's considered junk. Okay? Because let's say I open some device, right? The input starts popping out. I mean, what was it 0 before? Or was it what was it? Right? There's always going to be some transition state that's at least the length of your FIR filter. Yeah. You're just pointing in the sky. Okay. All right. So now you know how to compute convolutions very fast. Using if you know how to compute the DFT fast, then you can compute convolutions fast. But also remember this, that anything that you do with buffers, you can use one of these methods in order to make the result continuous. Okay, so think about in that sense, either by using overlap and save or overlap and add. And you'll see that when we're going to do in the labs. I mean, there's going to be, when you do anything that's real-time processing, you have to break it into buffers and perform some computations on it. Yeah. It's just a matter of implementation. Sometimes it's easier to do one, or sometimes it's the other. It's just the management of how I don't know. We'll give you this design freedom to pick whatever is more comfortable. But generally, there's no much difference between them. Okay, so one thing I want to kind of show a little bit of the subtleties of the DFT versus the DTFT. Remember, if we go back to the moving average example, we've got this periodic sink that is the DTFT of this moving average. And then if I performed a 5-point DFT, then I get a Dirac, which is just sampling the periodic sink here, and then at the zero crossings. If I do a DFT of 10, then I'm getting also samples in the middle, so that's why things are not zero anymore. But here's the question. What if I actually have the DTFT, and now I sample it, and actually make measurements that is less than 5 measurements? What happens then? What if I sample it at fewer measurements? What? What happens? What if the DTFT? If I have the DTFT, and I sample it, for DTFT of a sequence of length 5, I sample it at fewer measurements, like 4. What would happen?
You don't get the benefit of being able to determine its high frequency.
What if you have a sequence of length 5, and you compute the DTFT, and I sample that DTFT not at 5 points, which would correspond to the DFT, I sample it at 4 points, equally spaced. Can I go back and represent my original sequence? What? Not really, right? I start with 5 samples, now I end up with 4. From an information point of view, I lost something here, right? And I got some ambiguity. And effectively what you get is circular wrapping of that sequence, okay, onto itself. Okay, so this is kind of like the reality of aliasing. Okay, so now different places of the sequence are aliased on top of them. And I'm going to show you next time an example from MRI what actually works, what actually happens. So if I start with a sequence like this, and I can compute a DTFT, if I don't sample it correctly, I'm going to get that sequence, but wrapped upon itself. So I get aliasing, but this is kind of not the usual aliasing that you see, but it's like aliasing in the time domain. Okay? All right. Next time we continue talking about the circular convolution as a matrix operation, using it, looking at its eigenvalues, seeing that those actually are the DFT basis functions, and then move to how to compute the DFT fast, which is great. Okay? See you on Wednesday. And you're going to use this? And listen to Frank, because he knows what he's talking about. And please behave and talk to him too, so he doesn't feel alone. Okay? Make this as interactive as possible. Do you need this? No. It's not recorded.